Hello, my name is Ece Kamar. I'm a Senior Principal Research Manager at Microsoft Research at Redmond. Today I will be speaking with my colleague Besmira Nushi, who is also a Senior Researcher at Microsoft Research, and we are a member of a team called Adaptive Systems and Interaction. Today, it is our pleasure to talk about the work we are doing on responsible AI, in particular bringing responsible AI to reality, to the practices of Microsoft. With Besmira and I and many other colleagues at Microsoft, we have been part of a journey of implementing responsible AI at a company of the size of Microsoft and making sure that we are developing the right best practices, tools, engineering principles needed to bring responsible AI into reality. And today I will be talking about this journey with you, talk about the lessons we have learned on the way and how our learnings are influencing the research we are doing at Microsoft Research. Let's start with a quick outline. I will start with a quick introduction on responsible AI. Then I will talk about what lessons we have learned through the journey of trying to implement our work at Microsoft. And I will also talk about how this is influencing the research we are doing. Besmira will continue with 3 distinct tools that provide lenses into model performance. This tooling work is very important for ensuring that the systems we are building in the company are reliable. These tools are on error analysis, model comparison, and backward compatibility. We will conclude with a discussion on future directions. So just to start the discussion, in the last decade, we have witnessed big advances in artificial intelligence. And we see examples from these when we are looking into vision tasks, language tasks, or games where AI systems are now mastering. This is all very exciting as an AI researcher to myself, and it has been exciting for our larger community and for the world overall. Reaching human-level parity on these tasks and mastering games like Go or Pac-Man have created big expectations about the opportunity of putting AI systems into the real world. In 2016, some experts predicted that most radiology tasks would be automated by now, or we would have fully self-driving cars on the streets. Now, looking back in 2021, it is safe to say that the speed of moving AI into the real world has not been as fast or as easy as some experts have predicted. So why this is the case? Why the speed of acceleration into the real world has been slower or rougher than expected? When we look at examples of AI systems being applied to domains that matter for our society, like decision-making in courts, decision-making in healthcare, or physical AI systems that interact with people or could cause for humans, we see that how these systems function and, more importantly, how these systems make mistakes in the real world have consequences for people who are using them, people who are interacting with them, and for our society. An important requirement for an AI system acting in the real world is reliability. When an AI system is deployed in the real world, we expect that system to work as specified, as expected by its designers under many different conditions. When the lighting conditions are changing, when the use cases are changing, when there are unexpected conditions in which the system is being used, or when there are corner cases or outliers, and even most importantly, when we have different users, user groups, and sometimes these users may include underrepresented groups. These are all getting into the expectation of what we expect from a reliable machine learning or AI system. And reliability is a central principle that applies to every AI systems that are being developed to be deployed into the real world. However, in the real world, lack of reliability may manifest itself in different ways. When we are talking about reliability for a self-driving car, lack of reliability may manifest itself as a safety issue. For example, when a self-driving car, like in this example, may misrecognize some flags or pictures on the flags as stop signs and may start acting as if it is actually a stop sign. On an issue like face recognition, issues with reliability, the fact that these systems are not working equally well across different groups may manifest itself as a fairness problem and in fact as a problem around disproportional error rates. And even in cases where having lack of reliability may not lead to a safety problem or a fairness problem, these systems not working reliably across different use cases may create problems with user trust, users losing trust with these systems and stop using them. So recognizing that these reliability is a central concern to the development and deployment of AI systems in the real world, as early as 2016, Microsoft released its Responsible AI principles, and non-surprisingly, one of these principles is about reliability. So what are these principles? It's fairness, ensuring that the systems we are developing are fair, they are reliable, they are respecting people's privacy, and they are secure. They are inclusive for different people we have in our society. They are transparent when needed, and they are accountable for their mistakes. Of course, releasing these principles into the world is an important but easy part. Bringing them to reality and making sure that all AI systems developed in a company that is the size of Microsoft is the real challenge that we are involved with. To achieve this goal, at Microsoft, we formed the Ether Committee, which stands for AI Ethics and Effects in Engineering and Research. And researchers have been a central part of this initiative from the very beginning. For the last few years, I've been co-leading the work on reliability and safety, and also acting as a technical advisor for this effort, working together with many researchers from MSR, including Besmira Nushi, and also collaborating with different parts of the company. Since the inception of this Ether Committee, we have worked across the company to educate teams on the responsible AI challenges, to provide consultancy and support on specific cases, and develop guidance, tools, and best practices to enable practitioners in bringing these responsible AI principles into practice. And while we are doing this work, we are also very happy to see that our responsible AI ecosystem is growing at the company, because the success on a mission like this requires a company-wide effort and a mature organization spanning research, legal teams, and product groups. Today, Ether's research and development efforts in the company are supported by two sister organizations, one in our legal department, thinking a lot about developing a standard across the company and doing sensitive use reviews about how to develop our AI systems. We also have RAISE, an engineering arm that support engineering groups to implement our responsible AI principles and standards and bringing them into reality. And we are working closely with this ecosystem. So why did I tell you about what we are doing at Microsoft and our ecosystem? It's because I want to tell you about some of the lessons we have learned through this journey by working closely with our legal colleagues and also with our engineering colleagues. So the first lesson we have learned through the way: responsible AI emerges from understanding AI limitations in the open world. When we look into how AI systems are developed today and how people are talking about the success of AI, it mainly talks about lab conditions, where AI systems are tested on static test sets or on simulation platforms or games where things are pretty constrained. Here you are seeing a video of AirSim, a car trying to learn in this environment, and it is a pretty controlled environment, as you can see. However, what we are seeing case over case is that results we are getting in the lab, when it is nicely controlled and measured on static test sets, do not necessarily generalize to the open world, where we have outlier cases that are not necessarily included into the lab conditions. Here you are seeing a picture of a car driving in a different environment, much different than what AirSim, the simulation platform, was showing. And you can see here that this looks pretty different than the simulation environment I just shown you. Therefore, it is so important to have efforts in these AI training and development to leave the lab and get into the real world and have tools and work that focuses on how to ensure real-world AI reliability when these systems are deployed for real. So that is something we are going to be talking about today. Insight number 2. There is no single silver bullet to the responsible AI challenges that we are seeing across the different cases that we see. Why that is the case? First of all, developing AI, an AI system is much more than just training a model with some data. When we look into the AI lifecycle, we see that this lifecycle has many stages, from defining model requirements, data collection, data cleaning, thinking about the design, then model development, but then thinking about model evaluation, deployment and monitoring. Having these different stages mean that problems can occur at different stages of the AI lifecycle. So we have to support developers, designers, and the community at each step of this AI lifecycle. Second of all, we have to acknowledge that AI systems do not emerge separately from the human effort. We have to acknowledge that AI is developed by people, with people, and for people. What I mean by that is people are involved at every stage of this AI lifecycle. Therefore, it is important to educate them and also provide support to them at different stages. But another point that is coming from this sentence is that when we look into the application domains like hiring or medical spaces or legal decision making, the problems we see are not only technology problems, they are in fact socio-technical problems. The issues here are deeply rooted in the society we live in. So when we are thinking about developing responsible AI solutions, we cannot treat these problems as only technology problems. We need to be working with domain experts and need to reason about all of the stakeholders involved. This just makes our challenges a bit more complex. And the third insight, if we want to achieve our goals on responsible AI, we have to align our efforts with AI development and our AI developers. We have done a study which won the Best Paper Award in 2019 at this conference. In this study, we talked to more than 500 different machine learning engineers and developers at Microsoft, at our company. And we learned a lot of things. You can read the details at this paper. But they complain about the lack of tooling support, not having tool integration, being able just have to going from one experience to the next and to the next and to the next, and this creating fragmentation. But they also flagged some areas where we just have to put more effort into supporting them. And these include debugging. How do you know where your models are performing badly? Model evaluation and deployment. So when in the AI world, when we are thinking about AI tooling, most people think about tools that support model training. However, we need to expand our vision and think about all of the parts of the AI lifecycle where developers need support. And most importantly, some people may think that responsible AI is just something nice to have, something we need to worry about when we are deploying our systems. We disagree with this. For us, responsible AI is analogous to good engineering, and we have to work towards developing the right engineering principles and tooling and practices to be able to just have the same engineering rigor when we are developing AI as we are developing any other traditional software. And our challenge is that we need to figure out what these tools are going to look like when we are talking about AI systems. And in our investigations, we realized that the path to deploying reliable machine learning systems is still unpaved. So there's so much work we need to be doing, and that's great news to us as researchers because this gives us so much work to do, so many new problems to get excited about. So the vision we have for our work and the work that we are going to be presenting today is that we work on building tools and methodologies that help engineers accelerate the development iterations of the AI lifecycle. So what we are saying is that when we are thinking about AI reliability, we have to be thinking about a continuous loop. We have to identify where our systems are failing or not working as well as expected, diagnose where these problems are coming from, and mitigate that, and do this continuously as we are learning from the real world deployment of these systems. And by doing so, and by supporting teams in this cycle, then we can get faster at the work that we are doing, and we can be rigorous and systematic in our principles. So the three tools Besmira will be demoing today and talking about today are really about putting lenses into performance evaluation of AI systems. The first tooling on error analysis is going to be talking about the initial development. We have one model, one benchmark data, and how we are evaluating it. When we look into the current practices of evaluation, it is actually at its infancy. When we read AI papers or people talk about AI performance, they usually talk about one or a few aggregate numbers, like my system is 73.8% accurate. However, that single number is hiding so much complexity about model performance. When we look and examine models and their performance in more detail, we see that this performance metric is not uniform across the subspaces that this model is evaluated on. In fact, there are pockets of data where models are doing really, really good, and there are pockets of data where these models are not working equally well. And it is so important to have these lenses to these pockets of data where the performance is significantly differing, because by doing so, we will know where our models are reliable and where our models are not reliable, and also we can take the necessary actions to improve them and get into that continuous improvement loop. But we also see that model performance evaluation is not limited to one model. When we are continuously updating our models because we may have more data or we are switching to a new architecture, we usually check if our new model has a higher accuracy or higher aggregate metric than our baseline model. What we've seen in our work, and Besmira will be talking a lot more about this, is that just seeing these aggregate numbers going up does not mean that our next model is going to be better. In fact, when we look at the Venn diagram like this, what we see is that the new model maybe is improving on some things, but could also be regressing on some things. And a great motivating scenario for why we are doing this is the gender shades story, the research work done by Joe Boulamani and Timnit Gebru, where they have shown that for public models for predicting the gender from images, the models that are deployed in the real world could have very different performance across different groups of people on the dimensions of gender or race. So why we are seeing this proportional error rates for different subspaces of data? In the work that we have done in 2017, we have shown that this proportional error rates happen because the data, lack of representation in data, can break the fundamental assumption of machine learning, which is the training data has coverage for all of the cases that a model is going to be seeing in the future. However, when that assumption is broken, for example, in this case, we are building a classifier about cats and dogs, and let's imagine that some groups of dogs were not represented in training data, for example, small white dogs. What we end up seeing is that the model learning from this data has much higher error rates when they see, for example, white dogs, the subspaces that are not well represented in the training data. And when this happens, when our training data has blind spots, the models learning from data make mistakes in the open world that are called unknown unknowns, where they are making mistakes with high confidence because they are not really expecting these mistakes to happen. They are just their blind spots. In our 2017 paper, we have developed a framework, a two-stage framework, for debugging and testing these models. These two stages included descriptive space partitioning and a search algorithm with Marta-arm bandits. However, this technique was quite complicated. So what Besa is going to be showing you is follow-up work that actually makes a lot of these approaches really developer friendly. Why we are thinking about debugging? Because once we understand the errors in these models, then we can go and improve them. And this is exactly what happened with our face APIs once the research work identified these disproportional error rates. So after reading the paper from Timnit and Joy, the developer team went and collected more data to diversify the training data set. And as a result of that, now, back then, the models had improved very significantly for this task. So on this motivation, what I want to leave at is we need these lenses to be able to understand where our errors are so that developers can take the necessary steps at improving them. And this is the key to ensuring AI reliability. So now Besmira is going to be diving into the tree tooling that is making these principles developer friendly and bringing them to the real world. So I'll hand it off to Besa next.
Hi everyone, and thanks for being with us in this webinar. My name is Besmira Nushi, and I'm going to guide you through the tools that we have built for implementing principles for responsible AI. Ece made an excellent case for why responsible AI is indeed a must-have aspect for excellent and rigorous machine learning engineering. In order to support these principles and insights that we have shared so far, in the past years, we have worked closely with several teams at Microsoft to build tools that can help practitioners implement these principles, especially on reliability and safety. Now, we have a vision for supporting the whole machine learning life cycle from error identification to diagnosis and mitigation. The figure here maps the tools that we have built so far on this picture of the machine learning improvement life cycle. A lot of this has been internal tooling and infrastructure, and most recently we have worked on building these tools as open source offerings and Jupyter widgets. First, you can think of error analysis as a tool for supporting identification and diagnosis of errors. And then the two other pieces on model comparison and backward compatibility as support for closing up this loop and comparing models with each other, but also for mitigating regress issues by being able to train compatible models. So let's get started with error analysis. In fact, the work on error analysis started early in 2018 when we proposed a methodology for doing in-depth failure understanding for machine learning. Just like in the Greek tale, Pandora opens up the box of system inputs and it chops it in several semantic clusters. And then for each semantic cluster that is defined either via content features or the internal state of several machine learning components, then we build interpretable models that can explain when the model performs well and when it doesn't. So since then, we have advanced these ideas quite a bit. We implemented them as a tool, and now this is going to be open source. You can see the GitHub repository here, and we're happy to take feedback and also looking forward to your contributions. This tool consists of several visualizations that are intended either for doing identification or diagnosis. So let me show you how we use this tool for better understanding the benchmark on the gender shade study about which Ece just talked about. Now, something to notice here is that while the task may not be the most representative one for phase vision, it is a very good task for showing how certain societal biases can creep into models and how nuanced and complicated a story can be when it comes to testing for reliability. All the results that we are going to look together are results that are based on an old gender detection model, which was significantly improved after the gender shades paper came out. And we use the same data set, the parliament data set, that consists of photos of candidates of parliaments across Northern Europe and Africa. And then we also further augmented the benchmark with attributes that we either collected via human annotation, for example, hair length or whether the lighting in the photo is good or not. And then also from attributes from the Face Azure API that tells us whether a person is wearing glasses or whether they're wearing makeup and other face attributes. So let's see. Here we see a screenshot from the tool. On the left-hand side, you can see the meta attributes that were used to do error analysis. And then on the right-hand side, you can see a tree that was trained to best separate the errors from successes. So we are going to look at two different visual indicators. The first one is color. The darker the node in the tree in red, the higher the error rate is going to be for that node. And then the other indicator is the fill line. The fill line tells us how many of the errors that occur in the whole benchmark are actually concentrated in that particular node. So ideally, we would want to see these nodes that are not only in dark red, but they also have a high fill line. In this particular case, for this benchmark, we see that the base error rate is 5.5%. And then if we continue to follow this red critical path, then we can see that for women, the error rate increases to 11.5%. And then it increases even more if you are a woman and you are not wearing eye makeup in the photo. It increases even more if you also do not have long or medium length hair. And then the error finally becomes 35.7% if you're also not smiling in the photo. So we're talking here about an increase of 7 times in error for this particular group. And this, as you can see, this is a super complex pattern of error that is very difficult for the engineer to account for ahead of time without the help of automated tools. Now, let's go back and think about, suppose we found this problem. What happens next? And also, how is this pattern related to the fact that the model makes more mistakes for women with a darker skin tone? Well, now that we know these important factors for failure, then we can go and look back at the distributions of data for these particular factors. And this is exactly what we are showing in these graphs. We see that there exist dramatic distributional differences between women with a darker skin tone and those with a lighter skin tone. We see that women with a darker skin tone are less likely in this particular data set to have longer hair or wear makeup. And both factors contribute to an error increase. And this can give us really, a deeper insight about the story here. It means that we can do further targeted mitigation. Instead of just collecting data everywhere for this benchmark, we could target our data collection into these particular pockets. For example, for women with a darker skin tone that have shorter hair, or for women that are not wearing any eye makeup, in order to have, a more planned and informed mitigation plan. So as I mentioned, the tool is now in the open source. You can find it in this link. And something else that we did in order to boost the functionalities of this tool is to enable further diagnosis. One part of diagnosis is data diagnosis, which we showed with the distributional graphs earlier on. But yet another thing that you can do is to look at the most important factors for the model that led to that prediction. And so we are using primitives from the InterpretML library. This is also an open source tool for interpretability that helps us to identify the main factors, not only globally or locally for particular instances, but also for particular cohorts of data that are more problematic. In fact, for a better understanding, we are going to take a look at a demo together. Before the demo, I also want to thank our collaborators in Azure Machine Learning that made the open sourcing of this tool possible. Let's take a look at the demo. So the demo actually runs in the Jupyter Notebooks environment. You can import the error analysis dashboard from the Responsible AI widget. And you can call the dashboard by giving it as an input, parameters like the ground truth or the explanations for the data, or, for example, transformation of pipelines that you might have used if the data or some features are categorical. You can look at the widget here, but you can also open it up in a different tab in order to have a better visualization. So let's see. We first are going to go through the error identification visualizations. This is one of them, and it's similar to the three that I showed earlier for gender shades. And we can see that the base error rate for this task is 12.5%. In fact, the task that we are going to look at is based on a model that was trained on the UCI census dataset. And this data set has information on, for example, whether the age of a person, gender, education, and marital status. And the final task is to predict whether this individual is earning more than 50K or less than 50K a year. And this is a pretty common data set that is used in these settings. And now we are going to follow some of the critical paths that seem to be more problematic. For example, we see that for this particular pocket of the data, for example, for people who are married, they have a lower number of education years and they are older than 33, the error rate becomes 25%, meaning that it is doubling in rate. And we can also see that for this other cluster here, for people who are again married, they have a high number of education years and they are younger than 33, the error rate also increases to 28%. And perhaps this might be people who are married, but they might be still studying and they haven't had a chance to work yet. And again, this is an information that we do not have in the data set, but it's something that we can find out with these tools. Yet another error identification primitive that we can look at is the heat map. So in the heat map, we can see the dependency between certain features and error rate. For example, if I want to look at the number of education years, then I can see that for people who have a higher number of education years, the error rate becomes higher. I can again slice this with another dimension, for example, by gender. And we can see that these discrepancies in performance are higher for men in this particular case. So we can see that these differences are more visible for men. But then we can again do more and deep dive into particular clusters of data. For example, we can create a cohort that we may want to investigate further directly from the interface. For example, we can say that I want to look at this cohort later. And then this is another cohort that is only for individuals who are not married. And then I can continue to look at this data in the explanation side of things. First, I can do active data exploration. For instance, I may want to see how is the ground truth distributed. Basically, I am selecting the true Y here and also the distribution in the y-axis. And I can see that for the whole data, the data looks a little bit skewed, meaning that there are more individuals in this data set that are earning less than 50K in comparison to those that are earning more. And then we can see how this looks in particular for the cohorts that we just created. For example, we see that for the not married individuals, the story is again skewed, but perhaps a little bit more. And for individuals who are married, this looks more balanced, meaning that this can explain why the task of predicting income for individuals who are married becomes more difficult for the model, because this data looks a lot more different than the overall data distribution. Yet another functionality that I might have from the diagnosis side is to generate global explanations and to understand these factors. And this is basically what these graphs are showing us. And for instance, we see that both for the married and non-married cohort, marital status is important for the model because these values are high. But it seems that for the not married cohort, age is more important. And for the married cohort, capital gain is more important, meaning that the model is sort of treating these cohorts differently and taking different decisions. And then I can go ahead and I can look at local explanations for each particular data point. I can look at correct predictions, incorrect predictions, and I can, for example, pick to investigate one data point further if I were interested in. For example, I can pick this particular data point. I can generate what if explanations for this particular data point. I can look at if this person, for instance, had 15 years or of education, how would it change the prediction in this case? Is it going to make a change in the model? And in fact, we can see that the prediction changes. It becomes accurate if we change the number of education years. So again, this is the summary of what the tool can provide for you today. However, in the future, we are also thinking about further integrations. We also have other offerings from, for example, our lab in MSR New York on fairness assessments and mitigations. And in the context of responsible AI, we believe that the real value of these tools can come if we provide the frameworks where all of them interoperate together, and where the engineer can come in and use them without having to jump from one side to the other. So we have deployed the tool internally in several scenarios. When we look back at testimonials from our teams, then two main themes come up. The first theme is error identification. In this way, our teams say it is much easier to identify errors, and then it becomes difficult to overlook them afterwards if you have them in front of you with a tool. And then the other important theme is targeted mitigation. By knowing the heat map of how errors are distributed, it becomes more easier to do targeted mitigation, because then you can collect more data for that particular pocket instead of doing unguided and expensive data collection. Now, we are currently also continuing to do more research in order to increase the impact of these tools for supporting rich media, such as images and language. I will give you a few examples on each of these. For example, on the image side, the functionality of feature extraction or attribute generation is something that came up from our discussions with internal customers. We noticed that different teams may be at different levels of maturity. For example, some of them may have a lot of metadata available, but some of them may not. And if you do not have this metadata available, then by just looking at the images on failure cases and success cases left and right, it becomes difficult to understand what the pattern is. For example, in this case, you are looking at failure instances and success instances for a model that was trained on ImageNet on the particular class of image classification for detecting seatbelts. And the base error rate here is 33%. And again, we can look at these images, but it's hard to find any pattern. And so what we did is that we did more research on feature augmentation and extraction. Many of you may already know that the features that are extracted by deep learning models many times may not be interpretable or visible to the human eye. So what we did is that we employed robust models, because there has been recent research evidence that the features extracted by such models are more interpretable, and this is research that was done at MIT by Spiras et al. And what we did is that we checked how these features may be useful for doing error analysis. And we did feature extraction and then built custom feature visualizations to explain to the developer what these features may mean. For instance, in this case, you can see that for this particular two images, we have extracted these features that seem to be focusing, in this case, on grass. Even when we emphasize them, the photo starts to contain more grass. And then we make this available to the error analysis process and try to find patterns. So going back to the previous example on seatbelt, among all the features that we extracted, there was this one that was pretty predictive of failure. And in particular, if this feature was not present, we see the error rate to increase for the class of seatbelt. And when we visualize the feature, we can see that the feature represents human hair. And in other words, what this means is that this model had a difficult time to detect seatbelts when there is no human hair present in the photo, which in fact reveals a serious point of brittleness about the model if we were to deploy the model in the real world. Now, again, we can go back and look at these failure examples, and now we see that in fact there is either no hair in these photos or very little. And again, these are those types of failures that are difficult to find out if you just look at the images one by one, and this is where these tools may help us. We have applied this method for both robust and non-robust models. And in the case of non-robust models or standard models, you can think about this feature extraction as a content descriptor, basically something that can describe for you the input and then correlate those descriptions with the failure of the model. Now, on the language side, I wanted to mention a project that is led by Marco Ribeiro, also in our group. The tool is called Checklist, and what it does for you for language data is that it offers certain templates that can help you to understand the failures of language models, but also to guide your certain decisions that might be made in a large company about model release when it comes to large language models. And I suggest you to take a look as well. Let's continue with the next set of tools on model comparison and backward compatibility. Now, as Ece mentioned earlier, accuracy or aggregate accuracy alone cannot be the only indicator for us to take a decision on which model to deploy next. While we hope that our models will remain fully compatible and they will not introduce any new mistakes when we make an update, in practice, incompatibility and new errors can happen for many different reasons. They can happen because of optimization stochasticity, because the data may be different, it may have noise or distributional shifts, or just because, the new architecture may be fundamentally different from the old one. And so all these, concerns raise the need for considering these models, not just as isolated component, but to put them into an overall system perspective when we think about these models, not just as isolated components, but models that will work with other software components, or models that are going to work perhaps with a human. And therefore, we suggest to look at compatibility scores as well, except accuracy. For example, in this case, the trust compatibility score is a score that tells us how much trust was preserved during the update, meaning how many of the examples that were initially right are still correct. And then the error compatibility score tells us which portions of errors are not new. Now, we did experiments, and this is work that is led by Gagan Bansal at the University of Washington. And we saw that for cases, for example, like mortality prediction that was trained in a medical domain, we see that compatibility can be as low as 40%, meaning that 60% of the cases that were initially correct are now going to be wrong. And so what we proposed back then is to use a reformulated loss function that tells us, or that takes into account not only log loss as a measure of accuracy, but also the dissonance between the first version of the model and the second version. And in this case, in the new error dissonance, which is also the one that worked best for our experiment, basically we are adding an additional loss every time the old model was correct. And by using this type of regularization, then you can generate these exploration graphs between compatibility and accuracy in the y-axis. And every dot that you see in this graph is a different model. And so this becomes a tool for the developer to make an informed decision on which model to deploy. For example, they can say that perhaps I don't want to sacrifice any new accuracy. And so I may want to pick models that are in this flat area here. And perhaps if compatibility is an important aspect for my deployment, then maybe I want to go in this area. So we also think that backward compatibility can be a way for us to identify potential issues with the data. In this particular experiment that is part of our KDT paper that it was led by Mega Srivastava, here we see that even though we applied a data update, the data was much larger, we introduced this synthetic noise in label between car and truck. And after the update, we see that in overall, the impact is positive, which is the gray line here. But the classes on car and truck were most affected and from incompatibility because of the noise. And again, this becomes a tool that the developer can use to select the data in these histograms and look at what the label noise problem is there. So to package these ideas together into a usable tool, we started a collaboration with the Ether engineering team. And they have packaged this as a library and widget. And this is the GitHub repository for this widget. It contains the loss functions that I talked about, but also a widget visualization tool that we are going to see next. So this is how the tool looks like for backward compatibility. You can, here I have two classifiers, H1 and H2, and I'm doing backward compatibility analysis. The data set in this case is a data set that was trained in order to predict the credit score of a certain individual. And this is something that you may find applied in certain financial domains. And we have a choice to select, whether we want to do this analysis on training data or on test data. We can pick the dissonance factor in this case. And I can see that we have choice on many different models. For example, I can pick this model that seems to have like a good trade-off. For instance, this is the model that was trained with lambda 0, but if I look a little bit further, I can find even a better model. And then I can also focus on each of these and see how much regress and how much progress was introduced if I were to visualize this in the form of a Venn diagram. Basically, I am merging, the two types of errors together here, old model and new model, and see how much intersection there is in the types of errors and how many of the errors are actually disjoint. I can also see the distribution of incompatible points. For example, if I were to pick this model here, we see that incompatibility is sort of biased towards this particular class. So perhaps this is a model that I will not want to deploy, but maybe I am going to look at something more balanced like this one. It is also possible to use this in vision data. For example, this is an experiment that we ran on the MNIST data set. This is, again, two models. And now, as you can notice, here I'm using the widget just for model comparison. If I was interested just to compare these two models with each other. And I can look at the distribution in different classes. I can see that class 9, in terms of digits here, is more affected. I can click at this class and I can look at the particular instances that are incompatible one after the other. So I hope this gives you, a flavor of what these widgets look like. Of course, there is so much more that can be done with respect to model comparison and also error analysis, and we're looking forward to your contributions as well. To summarize our efforts, I also want to discuss, future opportunities and challenges along the way. We all have a vision on building end-to-end tool interoperability. There exist other challenges that we would like to tackle in the future related to connecting the data analytics story with model analytics, because this is super important. Data management perhaps has been a little bit detached from model analytics in the past, but now they are so close to each other, and we believe that these two stories need to be linked even more. The use of these tools needs to be interactive and scalable. As you saw, no analysis finishes with one click, and some of these experiences, they are useful exactly because they are interactive and allow you to dig more. To conclude, I want to say that if we want AI to keep its promise on economical growth and increase productivity, we need to prioritize responsible AI and the rigor that it brings to making our systems better. Here are a few resources for you to take a look at. I also want to introduce you to our group. In fact, there are a lot more people in our group that work on human-centered artificial intelligence and responsible AI. If you are a student that is looking for an internship or researcher positions, then feel free to drop us an email and we'll take it from there. So thank you, and we hope to see you in the Q&A. Feel free to come in and we'll discuss there. Thanks. Hi, everyone. Thanks so much for being with us here and attending our webinar on bringing responsible AI principles into practice with concrete tools and open source libraries. My name is Besmira Nushi, and I'm here together with Ece Kamar. Together with Ece, in the next 15 minutes, we're going to be answering top questions that you all have sent in our chat. And so with no further ado, let's get started. The first question that I'd like to pick here that Zeynep actually submitted in our chat is asking, does responsible AI sometimes go against company growth? Zeynep, this is a great question. We discuss about this very often in Microsoft, but also in larger forums. So the take that we are taking on this, as Ece also responded in the chat, is that responsible AI should be considered as a discipline that advocates for excellence in engineering. Many of the aspects that we talked about today, such as testing, debugging, doing proper evaluation on models, slicing and dicing the data, and looking at how our model performs in all these different subgroups, are directly related to the quality of service of our algorithms and models that we deploy in the real world. So responsible AI should not be considered as something that goes against growth, but as an initiative that goes in parallel with initiatives for increasing the quality of our services, increasing the coverage of our services, and also just, for us on the research side to be able to better understand what our models do and where we are going as a field. Ece, do you have a question?
I'll take the next question, Bessa. Thank you very much. And please have the questions coming. We are actively looking at the Q&A live stream to see what questions to take next. And I see a question from Lou that I would like to address next. Lou is asking, while many companies see potential benefits of developing responsible AI systems, there might be the responsible AI gap between principles and tangible actions due to the lack of knowledge of how to cross the gap. How do you think academia and industry can help reduce the gap? This is a great question, Lou, and this is something that we are thinking about every day at Microsoft because this is a real problem. One of the concerns here is that this is a pretty new topic for everybody in industry or in academia. I think nobody was really thinking a lot about responsible AI 5 years ago, and now this is definitely a big issue for a lot of us thinking about these problems. So what this means is that we are not at a very mature point in the understanding of these problems or providing solutions. This is why, as researchers, we are feeling very empowered at Microsoft because the ideas we have that we are putting into academic publications can turn into products under a year. This, error analysis is just an example of that. But other tools like FairLearn and Interpret ML are other examples of research getting into practice really quickly. So because of the very novel nature of the problems and the solution space, academia and industry can work together both in the understanding of these problems and coming up with solutions together. So this is a space where academia and industry can work a lot together. I think there is also an issue with awareness and accountability. What I mean by that is there are other problems we are just getting to know right now. And academics revealing these problems is definitely very useful. But accountability is another factor. We are dealing with some problems that do not have easy solutions. And academics or industry research partners revealing these problems and presenting them in the public also puts accountability for the industry that is developing these applications. So I think there are a lot of ways for academia and industry to work together. And also, I think in some long term, developing a responsible AI standard for the whole industry to follow so that we can all be on the same page about responsible AI. So Bessa, the next question.
Thanks, AJ. I'll respond to the most recent question here from Amina. They're asking, could we get any insight on any production or usage of these tools? And do you foresee any commercial use for these types of tools? So I can share a few insights about how these tools are being used within Microsoft. There are a few things that we have observed. We have observed that different teams can be at different levels of maturity. So, for example, there are those that have requests and asks for other types of functionalities, such as, for instance, the feature extraction functionality that I shared in the presentation. This was, really a request that came internally from these teams. And there are other teams that are at a level when they need more help in learning on how to adapt these tools in their everyday cycle. And we are trying, to support both. But it's something that one needs to keep in mind when building these tools, that you are going to be serving to different types of customers and practitioners. And we are actually seeing this also with the open source offering of the tools, in that also the external customers are going to be at different levels and requests. And this is something to keep in mind. On the commercial use, we are thinking at the moment of this as as a platform to serve developers, and the commercial benefit will come just from the fact that with these tools, we are going to be able to build better AI systems and models. And we are going to have a better coverage just by being more rigorous in the way how we engineer these systems. But of course, these tools are part of an ecosystem, like they don't live by themselves. And it is, we mentioned, other tools like FairLearn, there are data exploration, causal analysis, and so on. And as an ecosystem, there is a lot of value that they can provide to the community.
Great.
What else do you have in mind, Ece?
The next question, I will try to address actually two of the questions that I see in the Q&A, because I think they are related. So first, Indra is asking, could the techniques you discussed provide an understanding of dataset drift or concept drift? Let model developers know when a trained model has become stale or obsolete and needs to be trained on new data. That's a very practical question. And Kavuya has a relevant question. He's asking, can this tool be used to understand how backward compatibility and performance differs for non-supervised learning models? So both of these questions are getting into use cases of the error analysis and backward compatibility tools when the data set may not have labels or error labels in them. And the answer is yes. We can actually use error analysis tool to also understand how data is changing in time. Think about instead of now using error analysis with the error labels, but instead the labels you want to divide the data is whether this comes from the original training data or test data or the new data that is coming in. Or you can divide the data into temporal segments and now use the same decision tree and the matrix filter views to understand how the old data and the new data differs from each other. So now the label actually becomes the time segment of where the data is coming in. And now you can use the tools to find patterns that could separate how the new data is different from the old data. And through this, you can actually have interpretable patterns of data set drift or concept drift. So that's one use case the current tooling can be used. And we are working on some new visualization techniques that can make it even more intuitive to understand these kind of concept-drift issues. But even the current tools are applicable for those scenarios as well. And coming back to Kavio's question on non-supervised learning models, the same thing actually applies here. For example, let's say we are developing different kind of models. For example, models that are using different architectures, models that have different complexity, and we want to understand how these different versions of the models are different from each other. How are they making different decisions? So now the label we can use in understanding differences in error analysis could be the cases where models agree with each other and cases where models disagree with each other. So then again, we can learn now different patterns of behavior that are different between one model type and the other model type. And this is also applicable to the Venn diagram that Besa has shown for backward compatibility. So now we can actually look at, okay, what are the cases that models are working, giving the same answer, and what are the cases that they are actually differing? So a lot of these visualization techniques we have shown today are not only about supervised learning when there is a clear error label. With some creativity, you can use them for different data drift or unsupervised learning applications too.
Thank you, Ece. Yeah, so those are all very interesting points. Sometimes we run into this sort of, findings and discoveries just by visualizing the data better. On the backward compatibility example that Ece was giving, actually, I'm going to share like a story. We were working on our KDD paper on better understanding backward compatibility. And then we found out that by showing how backward compatible points are distributed in different classes or different subgroups of the data, this could serve us as a good indicator or as a diagnosis pointer for understanding also where noise, label noise was concentrated or feature noise. So if there was some distributional shift happening in the data, that visualization could serve as the first sort of like debugging point that could take us back to the data for us to better understand noise or other things that may have happened in the data set. So I'll be taking another set of questions. This came up several times, either on the questions on unsupervised models or, for example, on other data types that you might be working with. For example, there was a question from Arbor who was asking, can I use this for graph algorithms or are the tools particular or specific to a certain set of models? So the tools are built to be sort of a generic in the sense that they take the model as a black box, and as long as you have a notion of quality on the output of the model, then you should be able to be using the tools. However, there are many, other opportunities out there to adapt these tools and build more custom visualizations or feature extractions that better support certain types of data. We gave the example on feature extraction for images, but there are other types of feature extraction that one can think about, graphs, like putting in there the degree of the node or how connected the component is. Or if you're working on language, using ideas from the checklist tool that Marco in our group is working on and including them into error analysis. So there are a lot of opportunities out there to make these tools, more specific to the data type that you are working on. This is also one of the reasons why we are making these tools open source, because we acknowledge that the community is working, walking very fast towards advancements. People use different models, different data types. So if there is anything that you'd like, to build for your own model and data type, we're happy to take feedback, and also, feel free to send issues on our GitHub repositories or other proposals, or even contribute yourself.
Thank you, Besa. I'll take the last question if that's okay, and then unfortunately we are reaching the end of our time today. I've seen a few questions on the Q&A list that talks about whether these tools are the fundamental answer to the problems we have in responsible AI, whether data enhancement is the right approach or the only approach when it comes to addressing the blind spots we see in ML models. So I would like to cover a few of these questions together. So first of all, data enhancement is only one of the mitigation strategies that are applicable when we see these kind of reliability or bias problems in data. Other strategies could include reweighting of different groups of data in the training set so that we can retrain the model and see if models are getting better at paying attention to a certain part of the data. Or there are techniques that could modify the learning objective of these models to actually have a consideration in there to minimize the difference in error rates between groups. And the FairLearn toolset has some techniques already built in this. So what we are trying to do with the error analysis and backward compatibility frameworks is providing visibility to model developers to be aware of where errors are more concentrated. And of course, then they can take more informed decisions about how to best improve their models. And data collection is only one of these mitigation techniques. And we want to actually we are currently spending our cycles on thinking about these mitigations, and hopefully you will see mitigations being embedded into the error analysis workflows at the future releases. But coming to the question of, are tools the fundamental answer to the responsible AI challenges we are seeing? Definitely not. This is why at the beginning of the webinar today, I talked about our responsible AI ecosystem. And here we are acknowledging that the problems we are facing are not only technology problems, but they are socio-technical problems with components on culture and organization. We need to actually develop a culture in AI development that is aware of the impact that these technologies are creating in the world, and give comfort to teams to work on these very challenging problems that do not necessarily have simple answers. At the same time, thinking about what we are developing and why we are developing is a very fundamental question. I've seen a question earlier that talks about using AI as a weapon. This really gets to the use cases and the sensitive use reviews we are doing in the company. Again, there is no technological tool that will really address the question of the sensitive uses and the value judgments humans are going to be bringing to the table. So we have to complement the tools we are developing with the right culture, organizational structure, and human-centered processes that can really get teams to think about these hard problems. So with that, we are reaching the end of our time today. Besa and I would like to thank you all for attending our webinar. And this webinar will also be available on demand for listening to it afterwards. We appreciate your participation, your question, and your interest in the subject. And we would love to hear your feedback. If you get to use the tools and try them on your data, please email us. Our emails are available on the internet. So we would love to hear your feedback about the tools and how it has been useful for you, or what other functionalities you would like to see in the future. If you're interested in learning more, we have listed some great resources in our resource list. There you can read about some of the academic papers that have been the foundation for the work we presented today, get links to the tools, and also get links to some of the blog posts we have created that talks about some of the work and the vision for responsible AI. I would like to wish you a great day, and we hope to see you again at the future webinar. Thank you very much.